So now I will turn it over to Erin.
Yeah, thank you, Mr. Dolan. And it's so nice to see everyone tonight. So it's my pleasure tonight to introduce Professor Meg Urry. As some of you already know, I'm a junior astrophysics major at Yale. And Professor Urry was actually the very first astro professor I talked to in college. So I had reached out to her because other students raved about how approachable and supportive she was, and because I was interested in black holes at the time. She was more than happy to take time out of her busy schedule and invite a young freshman me to her office to speak. And it wasn't until months later, after we had talked, while I was at a conference for women in college studying physics, and everyone kept asking me if I knew Professor Urry and what she was like, that I realized what a big deal she is in the field of physics and astronomy. So Professor Urry is the Israel Munson Professor of Physics and Astronomy and Director of the Yale Center for Astronomy and Astrophysics. She served as chair of the physics department at Yale from 2007 to 2013, and in the presidential line of the American Astronomical Society from 2013 to 2017. Professor Urry received her PhD in physics from Johns Hopkins University and her Bachelor of Science in Physics and Math from Tufts University. Her scientific research focuses on active galaxies, which are home to supermassive black holes at their centers. Professor Urry is a fellow of the American Academy of Arts and Sciences, the National Academy of Sciences, the American Association for the Advancement of Science, the American Physical Society, and American Women in Science. She's received an honorary doctorate from Tufts University and was awarded the American Astronomical Society's Annie Jump Cannon and George Van Weisbroek prizes. Prior to moving to Yale in 2001, Professor Urry was a senior astronomer at the Space Telescope Science Institute, which runs the Hubble Space Telescope for NASA. Professor Urry is also known for her efforts to increase the number of women and minorities in science, for which she won the 2015 Edward A. Boucher Leadership Award from Yale and the 2010 Women in Space Science Award from the Adler Planetarium. So that was a mouthful, and maybe big deal might actually be more of an understatement when describing Professor Urry. But on a more personal note, I am forever grateful to Professor Urry for the impact she probably doesn't even realize she's had on my undergraduate education. Many times when I felt like maybe physics isn't right for me or that I'm not smart enough for it, I just happen to end up in a meeting with Professor Urry or see her give a talk, and I'm reminded by her words that I am good enough and that I can do this. It is in large part because of her hard work and activism that I get to be surrounded by brilliant and talented female physicists every day I'm at school, which unfortunately isn't the case in many other physics departments. She continues to show others the importance of mentorship at all levels, and is part of the reason I prioritize teaching and love working with younger students. I hadn't heard about the Global Teaching Project before coming across the application to be a tutor online. When I found out Professor Urry was the founding physics instructor for this very program we're all doing now this summer, I knew it must be an amazing program, and I applied immediately. So we're all lucky to have her back with us tonight, and I hope you guys have some great questions to ask her later on. And with that, I'll hand it over to Professor Urry.
Wow. Erin, thank you so much. Honestly, your remarks are so nice, and it's hard to live up to. So we'll just try to get the universe to help me, because what I'm going to talk to you about is how physics is helping us understand the universe we live in. I do astrophysics, and you know, if you had told me when I was your age that frankly you could have a job where someone pays you to study what's out there, I just would not have believed it for a minute. I'm one of the most fortunate people I know in terms of having a job I love and getting to spend time with students. Erin said, you know, I took time out of my busy day to talk to her. I don't remember actually that it was, but I'll tell you, I prioritize talking to students because that makes me happy. Teaching makes me happy. I do a lot of other things, not all of which makes me happy, but students are the best. I mean, there's nothing more satisfying than explaining something to somebody and having them suddenly grasp it. I'm sure you've all seen that. Like if you have a classmate who is having trouble with a problem, or you're doing your homework together with somebody else and the two of you manage to figure it out together, there's just this happiness about suddenly understanding something that was opaque before. So that's what it's all about. Anyway, sorry, I don't mean to philosophize. Let me shut up and just get with the program here. Okay, I'm going to share my screen with you. And this, I have a few slides that I'm going to show. I think, can you also see me when I'm talking?
Yes.
Yes. Okay. That's
Yes,
also
ma'am.
That's good. A little unusually, I thought I'd just take a couple minutes and tell you who I am. I mean, you just heard who I am now, which is fancy schmancy Yale professor with some honors. You know, I was a kid like you. I grew up in Indiana. I was born in St. Louis, Missouri. As a kid, I lived in Indiana, West Lafayette, Indiana, or Lafayette, as they say. And then when I was about 12, we moved to the Boston area. I lived there for until I went to college. And I was a good student. I liked school, but I wasn't particularly interested in science. If you'd asked me what I was going to be when I grew up, it probably would have said I would be a writer or a diplomat or, I don't know, mathematician, something. But I wouldn't have said scientist. I thought science was kind of boring the way it's taught in elementary school, middle school, even high school. I took physics as a junior in high school, and I really hated it. I have to tell you, I didn't know why we were doing what we were doing. It made no sense to me. And when I got to college at Tufts, I did take physics. And oh, I forgot, I was going to advance the slide. Oh yeah, this is me then. So like, you're not looking at this old lady. That's not quite college. That's a little after college, but still, it's a little easier to relate maybe. Also, I used to wear really wacky earrings. Now I'm very conservative, but you know, these are flying pink plastic elephants. I don't know if you can tell, but I was kind of a little goofy. And I took physics as a freshman in college, and it was harder than anything I'd done before, particularly when we got to electricity and magnetism, which are kind of abstract concepts that I didn't have any intuition for. And I just got sort of angry about it. I mean, I would listen to the professor and I'm like, what are you doing? I don't know what you're doing. I don't know why you're doing it. It makes no sense to me. And that was a moment when I could have just said, okay, physics is not for me. But something made me stick it out. Something made me keep going. And partly it was that I thought, look, this cannot be that hard. There are many, many people who have mastered physics, and surely I can get this. So I ended up kind of teaching it to myself, studying hard, and suddenly it clicked. Again, this moment when things that had made no sense suddenly come together and make sense. And I realized that some pretty simple concepts, physics concepts, govern, you know, the universe around us. And suddenly walking down the mall, shopping mall, you know, dodging people became an exercise in gauging velocity and acceleration. And it just became fun. It was clean. It was clear. Nothing against other fields. Matt was a history major at Yale, but history was arbitrary. You know, if Professor A said, this is the cause of that, and Professor B said, no, it's some other cause, you could just argue forever and you'd never know. Whereas in physics, there's a right answer, you know. So I kind of like that. I kind of like the exactitude. So I stuck it out, and that led to this career I've had in astrophysics. I had a research job as an undergraduate where I worked with a British astronomer who had just done a survey of the sky, and he found things we call quasars, which have supermassive black holes in them, and all this exotic, amazing stuff. And again, I just thought, really, this is not work. This is fun, figuring out what the universe is made of. And that's how I got started. And it was hard along the way, particularly being a woman in a field that was essentially all men, being the only woman in the room. It's different now. There are many more women, but there are not many people of color. And I am very conscious of the fact that being alone in that way is also difficult. But all these things are changing, and we're, I think, improving as a field, and bringing more people in helps a lot with, you know, just making the talent pool richer, and making the exchange of ideas broader and stronger. So it's all good, but we have to keep going. Anyway, so I just want to say, I'm sorry if this is way too philosophical, but just, you know, if you start to feel like you can't quite get this, it's hard, I would just ask, maybe try it a little bit longer, because there are some real rewards to cracking the code. Okay, enough of the young Meg here. Let's talk about the universe. So this picture that you're looking at, which if you are in a room where you can turn the lights out, it's even better. Turn my lights out? Yeah, it's better with the lights out. Is a very deep image of the sky taken with the Hubble Space Telescope. It's called the Hubble Deep Field. And what you're looking at is mostly galaxies. Almost every object in this image, these fuzzy things, are galaxies, which are collections of stars. I'll say more about galaxies as we go, but there are hundreds of millions of stars bound by gravity into galaxies. And that's most of what's in the far reaches of our universe. It's also what we live in. We live in a galaxy. We're going to zoom in on this picture a little bit and look a little more closely at these objects. You see some objects with spikes. Those are point-like objects. Then the optics of the telescope make those spikes appear. They're not real, but that tells you you have a point of light. Whereas you see these yellow things are more fuzzy. Those are relatively nearby galaxies. Astronomers would call those red. Yeah, they're not really red, but they're not blue, so they're red. This picture really summarizes what I think is interesting, what I work on, which is what is out there? What is the universe made of? How did it come to be like this? And it turns out most of that, all of that, is governed by the laws of physics, which we can understand really in a first-year physics class, like an AP physics class. So I study here, I mentioned the Hubble Space Telescope. I used to work at the institute that runs a Hubble. It's in orbit. This is a picture taken from the space shuttle early in the lifetime of Hubble. It was launched in 1990, which is before almost everyone on this call was born, and has been operating now for 30 years. It's not a huge telescope by modern standards, but because it's up above the atmosphere, its imaging is extremely sharp and the skies are very dark. So the quality of the pictures is very, very high. Hubble has a successor called the James Webb Space Telescope, which is considerably bigger. Hubble is about 2.4 meters in diameter. That's around 10 feet. And the James Webb telescope is 6.5 meters across, which is more like 25 feet across. And this will be launched in about a year and a bit from now. It's been built, it's ready to go, and it will be, the bigger the telescope, the more light it can gather, and therefore the more detail about the distant universe in particular. We also use ground-based telescopes. These are the two, you're looking at the two domes that house the Keck telescopes, which are identical 10-meter telescopes. And just to the left of the left white dome, you see behind it, that's the Subaru Telescope, a Japanese telescope. All of these are on the summit of Mauna Kea, an extinct, we hope, volcano in Hawaii. Just to give you an idea of size, this is a mock-up of the Keck mirror, 10 meters across, with a bunch of people who helped build it. So you see that it's really big. When you see it in person, it's extremely impressive. And in fact, and here is the summit of Mauna Kea, picture from the summit, showing a bunch of domes for a bunch of different telescopes. You see in the sort of the right-hand side of this, oh, I can use my mouse, can I? Can I use my mouse? Yes, I can. Here are the two Keck telescopes. Here's the Subaru Telescope. I think I've labeled them. Yeah. Various telescope facilities. Why? Because this summit is at 14,000 feet above sea level. So the air is very thin and clear, and the skies are clear most nights, and the quality of the seeing, the sharpness of the images that we get is extremely good. It's one of the very best sites in the world. It's also very dry. As you can see, there's not a lot of greenery, and that dry air is also important for astronomy. So back to this picture, what are we actually trying to find out when we make pictures like this? And one of the things we're doing is studying galaxies. But let me pause and show you a little cartoon which illustrates the size and scale of the universe so that you get a sense of where I'm talking about in the greater scheme of astronomy. So in this picture, if you look at the lower right, you should recognize the Hubble Space Telescope there. That telescope is, as I said, about 10 feet in diameter. So this dimension is about 10 feet, and this length is about 10 meters, which is roughly the diameter of the Keck telescope. And down here, I hope you can see two little astronauts to give you a sense of scale. So this thing was the biggest telescope that could be launched in the space shuttle. And it has, as I say, a rough size of 10 meters. The idea of this cartoon is that we multiply each size scale by, in this case, 1,000,000, and we get to a box, this box that's 1,000,000 times bigger than Hubble on the side, 10 to the 7th meters, would enclose the Earth. So the Earth is about 1,000,000 times bigger than the Hubble telescope. And if I multiply again by a factor of 1,000,000, I get to the size of the solar system, 10 to the 13th meters. Solar system is our sun is the star at the center of it. And planets, 8 planets, used to be 9, but Pluto was demoted. 8 planets orbiting the sun. Earth is the 3rd planet out. Okay. That number, 10 to the 13th meters, is kind of abstract. So another way of thinking about how big that is how much time it takes light to travel that distance. And roughly speaking, for light to travel across the solar system, say from the sun out to Pluto, is about 10 hours. Okay, so we would say the solar system is about 10 light hours across, or 20 if you want to double for diameter. Okay, let's multiply now by a factor of 10,000, and we get a cube that encloses the nearest stars. The stars closest to our sun, they're a few light years away, but this is still super close in the neighborhood. Those stars are part of the 100 million stars that are in our Milky Way galaxy, which looks something like this. This is a spiral galaxy. We multiplied again by 10,000. And now we have a galaxy which is 100,000 light years across. So we live in the outskirts. Our sun is a star out in the outer part of the galaxy. So if there are planets in our galaxy, there's 100 million stars in the Milky Way galaxy. So the chance that there's one with planets that have life is actually pretty high. But if that life has developed to the point where Earth is, where you can communicate, sending radio signals out into space, the idea of having a conversation is unlikely, because our message, we've been sending messages out inadvertently. It's called TV. We've been broadcasting TV since the 1940s. So all our stupid sitcoms have been going out there for decades. But they take, tens of thousands of years to get across the galaxy, 100,000 years to get to the outskirts on the far side. So even if someone intercepts those signals and says, oh, what a great show, let me compliment them, and sends a signal back to us, we're long gone by then. It will take another 100,000 years to get back. And then 200,000 years from now, somebody will get a review of, the honeymooners or whatever. Okay, nobody knows what the honeymooners is except Matt, who does. Okay, multiply now by a factor of 100, and we get to a cube that encloses the nearest few galaxies. Our Milky Way galaxy and the Andromeda galaxy are the two massive spirals that are in this volume. And most of the rest, maybe 100 or so, there's 100 tiny little galaxies, some of which basically are falling into one or the other of these two galaxies. We've already eaten up several small galaxies over the last, not yesterday, like the last couple 100 million years or so. Okay, last multiplication by a factor of 1,000, and now we're on the scale of the entire universe. And here we're talking about 10 to the 26 meters, or roughly speaking, 10 billion light years across. So from the most distant galaxies to us today, light has taken about 10 billion years to reach us. That makes astronomy a little bit like archaeology. When we look out in space, as we look farther and farther away, we see the universe as it was millions and billions of years ago. So the galaxies that I study and the black holes that I study are on this largest scale. And in many cases, I'm looking at those galaxies as they looked 5 or 10 billion years ago, when the universe was much younger. So we're looking at our baby pictures. At the same time, we can study the universe near us, that's our present, and the distant universe is our baby pictures. Okay, so what I study specifically are galaxies. I'm showing here just a montage of different kinds of galaxies. And just to point out, like the upper right-hand picture, this one is a spiral galaxy. That's because it has these spiral arms. Lots of gas-making stars and dust. You see these dust lanes are these dark parts. Here's another spiral galaxy here. This one has a bit more of a bulge. That's a bright sort of circular, or not circular, spherical distribution of stars in the center. Here's a galaxy that's mostly bulge. It has a disk, but it's got a lot of stars in the bulge. Let me explain that all the light you're looking at is coming from stars. You see a few individual stars. Those are in our galaxy. We have to look past those to get outside our galaxy. So they sort of pollute the picture of the other galaxy. But the smooth light that you see, oh, that's interesting. The smooth light that you see, you cannot see the individual stars in the distant galaxy. I want to point out a couple more things. First of all, color tells you something about the age of stars. So the bluer the light, the more young stars there are. The redder the light, the older the stars are, or the more dust there is, or both. And one more cool thing to point out is, you see this picture here are two galaxies that are in the process of merging, and they're gravitationally distorting one another. And the same thing is happening in the upper left. You see these two galaxies, they look a little odd, and that's because the gravity of each one on the other is stretching the galaxy apart. It's called tidal forces. These happen when two bodies are close to each other relative to their size. So the near sides of them pull harder on each other than the far sides, and that makes each of the objects stretch. Again, stuff that's explained by the gravitational physics that Newton figured out 400 years ago. Every one of these galaxies has a supermassive black hole right in its center. This is a black hole that's maybe 1 million to 1 billion times the mass of our sun. And most, as I say, every galaxy above a certain mass has one in the center. We think they grew over the last 10 billion years by consuming material that's pulled in by gravity. And again, there's a physics concept here. Matter doesn't just fall in. It's not that easy. The concept of angular momentum, which you may have learned about, prevents matter from falling directly into a black hole. It orbits it instead. And it has to lose angular momentum before it can get into the black hole. You are familiar with this in the sense of, I talked about the planets orbiting the sun, right? The sun is very massive, It exerts a very strong gravitational force on the Earth, but the Earth's not falling into the sun directly. It's going around the sun, and that force of the sun is keeping it in orbit. But fortunately, we don't lose a lot of angular momentum because our orbit is very friction free. So the Earth's going to go around the sun for a really long time without falling in. And it makes it a little hard for black holes to grow, but that's one of the things we study is how does that work and how can they grow? Okay, so now I'm going to show you a movie. This movie is a computer simulation. So it's a calculation done in a computer, starting from conditions that we think existed in the very early universe, the distribution of matter. And that's what you're looking at, is sort of the density of matter in a representative region in the universe. If you can see the label on the lower left is telling you the time since the Big Bang, which is when the universe was essentially born. And it's here we're at about 2.5 billion years after the Big Bang. And you see that matter is getting clumpier and clumpier. That's the action of gravity over several billion years. At this point in the movie, the color scheme is changing. Now what we're looking at is not density of matter, but temperature of matter. So white is very hot, red is hot, blue is cool. And what you're looking at, these things that look like explosions, big bombs going off in the centers of galaxies, that is the energy released when a black hole is growing. As matter falls into the black hole, gravitational potential energy is converted to outflows or heating of the gas around the black hole. And that's what ends up looking like these bombs. Now it looks like bombs because we're going fast here. You know, we're up at 7 or 8 billion years since the Big Bang. So this is not real time. I've sped it up for your convenience because dinner would take too long otherwise. For the final bit of the movie, the new color scheme, the purple color scheme, is showing you the chemical enrichment of the intergalactic medium. Every time I forgot, I'm going to back up. Can I back up? Yes, I can. I forgot to say something. So let's go back and go again. Yeah. So back when we're still talking about temperature, now look carefully and see if you see little flickering. Forget the big bombs and just look. You should see some little flickering, which are tiny explosions of stars. I'm not seeing any. Okay, sorry guys. I'm a teacher, so I got to show you this again. I'll have to cut some off the end. All right. Somebody with eagle eyes. Yeah. Here was some flickering, some little flickering. Those are stars that reach the end of their life and they explode. And when they explode, they send all the material in them out into the galaxy. In the interiors of stars, hydrogen has been converted to carbon, nitrogen, oxygen, heavier elements, and those are now polluting the intergalactic medium. So the purple scheme is showing you where there's high chemical enrichment is white, and low chemical enrichment is the dark. So all of these elements are being sent out into the galaxy by exploding stars. Those elements are what you are made of and what the Earth is made of. Every single carbon atom in you was made in the interior of a star and exploded out into the universe. Earlier in the universe, and then later in time, it formed a planet, Earth. And then that Earth carbon, you know, you ate it when you ate some lettuce. So that's how you are alive. The oxygen that's in water and carbon is why you're alive. Okay, here's another computer simulation. This one just focuses in on 2 galaxies that are going to merge. And again, we've sped this up for your convenience. The entire merger that you'll see over the next 60 seconds or so is takes about 200, 300 million years. And what this movie does very nicely is show you the computer simulation, this one, compared to a real pair of galaxies that we observe in the sky. Of course, we don't see a whole merger because it would take 300 million years, which, you know, we don't have, but we can see the different stages of the merger in real galaxies that looks exactly like what we simulate in the computer. And this simulation is really just gravity and stars. That's how it's calculated. So one of the jobs, if you like, that astrophysicists have, some of them are computational astrophysicists. They make programs that calculate these kind of things, these mergers. And I think that may be the last one. This is the antenna galaxy. And these great long tails, these are called tidal tails. These are signs. If you see a galaxy with these great long tails, you know it's in the process of merging, and in fact, near the end of a merger. Okay, and here's an example of two galaxies that are clearly interacting gravitationally, and the tails tell you that they're significantly affecting one another. I think this one's called the mice because it looked like two mice with long tails. So back to my galaxies, now you recognize the merger signature, the stretching part. I forgot to say, but after two galaxies merge, the bulge gets bigger. So this galaxy in the middle with a huge bulge has probably had many mergers. And a galaxy like, like this one down here on the left with not much of a bulge, this probably has had almost no mergers. So looking at galaxies, we can tell a lot about them. And this is the end of my talk. I just wanted to mention what my group does, my research group. What that means is I have students, I have graduate students and undergraduate students and occasionally high school students working in my group, and sometimes postdocs. And we use space telescopes. I mentioned Hubble before, but there's also the Chandra X-ray Observatory, which detects much shorter wavelength light, and the Spitzer Space Telescope, which detects much longer wavelength light. And we use these in combination with ground-based telescopes to measure the emission from galaxies and to find black holes that are growing in the centers of galaxies. And my group, just to get to the bottom line, I'm not showing you all the details of how we did this over the last decade and a half, but we've found many previously hidden black holes that were not seen with previous surveys. We've confirmed a sort of growth spurt of black holes in the early universe. From a period of about 5 to about 8 billion years ago was when most black holes and actually most stars were forming. And how that energy that's thrown out into the universe from the growth of a black hole must have a big effect on the galaxy it's hosting it. We haven't yet found how exactly that energy is transferred to the galaxy, and that's the project, a project that we're currently working on. So all of this stuff I've showed you, I hope you sort of see it's kind of fun to figure out. It's very cool stuff. And then beneath it all, helping us understand what's going on is really just the physics you're learning now. The physics of gravity, the physics of electromagnetism, which is which describes light and how it travels and how it's produced. While physics itself can be sometimes a dry subject, what it explains is basically everything. You could have a biophysicist come in and explain how your cells work based on physics. You could have a chemist come in, and the physics of atoms is what chemistry is. And really any science you can think of, physics explains everything. I'm a little biased, I get that. I'm a physicist, but I think it's a really useful thing to learn. So that's what I had planned to say. Let me stop sharing, and what I'd like to do is hear from some of you and perhaps answer your questions.
Well, thank you, Meg. That was great. My son, as Meg well knows, my son graduated a few weeks ago from Yale. He was a physics major there, which is why I have my cup.
Excellent.
Even though I was a history major. So what we want to do now, a number of you have been putting in questions. We really appreciate that. I think there's some very good questions, some about black holes, some about what one needs to study in order to prepare for a science major in college, etc. What I'm going to do is turn this over to one of our supervising instructors, Anna Creekmore, and she will manage the questions. As some of you may recall who are on with Professor Weiss some time ago. Anna served the same role. And if questions occur to you, please just type them in the chat box, and Anna will recognize you and will convey your question. So please, whatever comes to mind, just type it in. So Anna, if you could please take it over.
Okay, Dr. Urry, one question that we've had multiple times is, would you mind speaking towards, like, what do you think about the ACT and what score they should be shooting for, or kind of your perspective on standardized testing like that?
Oh, wow. Okay, I won't go into my rant. Let me just say, I wouldn't put too much power in the ACT or the SAT or whatever. You know, these tests were invented as a way of assessing how the level of work high school students are doing, because grades are uneven between schools. But really what they should be used for is to predict performance in college. And they have they're very uneven predictors. So I think there are people with very, very high ACT scores who make great scientists and some who don't. And there are people with low ACT scores who make great scientists and some who don't. So I wouldn't let it be too big a deal. Several school systems are dropping them. And personally, I would like to see them de-emphasized, because I think much more of success in life and certainly in science is our personal skills, like your motivation, your determination, how hard you work at learning things that initially seem hard. Those are much more determinative of how you'll do. So I'm sorry if that isn't quite on the point, but yeah, I'm not a huge fan of standardized tests.
And I don't mean to take any of Meg's valuable time, but I will say that the fact you are on this call, the fact you are in this program 4 months after schools have closed, during your summer, taking on a rigorous subject matter, the fact that we hope to see all of you at 9 a.m. tomorrow, that speaks very, very well about your potential for doing very solid work at the next level. Because it, as Meg says, it all starts with work ethic and a good attitude. And the fact that you're part of this program and the fact you're on this call speaks well about that. So
just showing up is 90% of what you will have to do in life. And with that, Meg, you can feel free to keep going, but showing up is what matters most. Yeah.
Our next question is from Demiria Moore from McAdams, I believe. She asked, what happens to matter when it's absorbed into the black hole, if matter can't be destroyed, especially?
Mm-hmm. Yeah. So it helps make the black hole bigger. So you may have heard of them. They're like the Roach Motel, right? Matter goes in and it doesn't get out. And as far as we know, that's still true, that black holes, once matter is in, it cannot get out. That's pretty easy to understand in simple physics. So let me just, so if you go outside and you throw a ball into the air, it will fall back down. That's because of gravity, okay? If you could throw it harder, it would go higher, but it'd probably still come back down. But if you were NASA and you could launch it with a rocket, it could actually escape the gravity of the Earth. And the velocity with which you need to throw it up so that it doesn't come back down is called the escape velocity. From the surface of a planet or wherever, it's the speed you need to get away to infinity, to escape gravity. For a black hole, the escape speed is the speed of light or greater. So since matter can't move faster than the speed of light, there is no way you can throw it hard enough to get it out of the black hole. It's stuck in there. So as matter falls into the black hole just grows more and more massive. And we can see that early in the universe, there are some extremely massive black holes, but probably most of them are quite small because it takes time. It takes billions of years for them to grow big enough. Some of the energy can be transferred. It can, as the black hole, as the matter is falling into the black hole, it can transfer energy out, but once it's in the black hole, that's it, nothing comes out.
Thank you. Okay, our next question is from Jeffrey Gary. He asked, does the size and lifetime of a black hole depend on how much matter it consumes?
Absolutely, absolutely. So over time, black holes in nature will get bigger. In principle, black holes can lose mass. I actually kind of sneaked by that because in normal nature, they don't. But let me just explain this to you. So there's a process by which black holes can, in principle, evaporate. It's a quantum mechanical effect, again, more physics. In quantum mechanics, nothing is ever quite fixed. The universe is quite a dynamic place. And so in a completely empty region of space, all the time, nature is making pairs of particles that annihilate. So out of nothing, you can have an electron and a positron created. As long as they annihilate, they meet again in a very short time. There's a whole branch of quantum mechanics that describes this. So Hawking and others talked about a process by which, imagine a black hole that has right outside it this empty space, and a pair of particles is created, and one of them falls in the black hole and the other one gets away. If that happens, what effectively you've done is create a black hole that has a particle escaping from it. And so that's a process by which, if you could do that over and over and over again, you could reduce the mass of the black hole. But what happens in nature is that process may be happening, but for every particle that escapes, there are gazillion particles that fall in, because nature is not an empty place. There's lots of matter around. And so in nature, black holes only grow. And the reason I went through all that and told you, you may have heard of, well, I don't think you're old enough actually, but there's a particle accelerator in Switzerland called the Large Hadron Collider that has been running now for almost a decade. And when it first turned on, people were afraid, because it creates particles with very high energy, that some tiny black holes might be created. And if you created a black hole, maybe it would just suck up the whole Earth and we'd all be done for. Happily, that didn't happen, as you can tell, because we're all still here. But also it wouldn't have happened. And the reason is because those black holes would have been so tiny that they would have evaporated before a particle could fall in and make them bigger. So we were safe actually from those black holes, as you can tell, because we're here.
Okay, Isaiah Townsend wants to know, how many galaxies are there total?
Good question. If you'd asked that even 10 years ago, we probably wouldn't have had a great answer. But now, probably 100 billion. There's probably about 100 billion galaxies. It's a little bit of a trick question in the sense that the definition of a galaxy becomes fuzzy as you go way back in time to when the first stars were forming. They were forming in clumps. So do you call that clump of stars a galaxy, or do you wait until it's above a certain mass? So it's not a hard and fast number, but there's probably hundreds of billions of galaxies in the universe. And we can tell that picture I showed, that the Hubble image of galaxies is like a census. Only it's not the US Census. The US Census tries to count every individual in the US. When we do a census, we look at a representative part of the sky, count what's there, and then extrapolate to what's in the entire universe. And that's how we get that number of 100 billion, couple 100 billion galaxies.
Our next question is kind of from Trindarius and Jasmine both. They wanted to know what classes should they be taking now to kind of get them prepared, and maybe what they should major in if they wanted to consider a field similar to yours.
Ah, cool. So I think the most important thing to take is math, actually. Math is really useful for everything. and it's the language of physics. So math and physics are like foundation, and you can build anything you want on them. I sometimes talk about astrophysics as a gateway science, meaning that, you know, it's something that everybody thinks about if you've ever been outside, not if you live in a city with a lot of lights, but if you've been outside on a dark night and looked up and seen the sky, you think about what's up there and what it means and where it's from. And thinking about that gets you naturally thinking about a lot of questions about how the Earth came to be, or how the oceans came to be, or why the North America is sitting on this part of the planet when, by the way, all the continents used to be together, and so on. So it's just part of asking questions about where we came from and where we're going. And physics and math are really foundational in any of those fields. So those are the things I think are probably most directly useful. On the other hand, you know, to be a good scientist, you have to be, well, nobody is good at everything, but people who are good at writing papers, that's a real talent for science, being able to communicate what you did clearly and tell your results, or being able to give talks about it is really useful. So being a good speaker, which, by the way, almost no one is born being a good speaker. It's something you can learn how to do. In fact, everything is something you can learn how to do. You know, a good friend of mine once explained that the modern academy, you know, universities and colleges, grew out of monasteries in Europe. That there's a direct line from how we run our universities today, from monasteries in, you know, medieval Europe. And some of the unfortunate parts of that origin are that people think you have to be born with a calling, that you have to be born already knowing you want to be a priest and how to do it. And there is, unfortunately, that mindset sometimes in science. It's completely wrong. You can learn everything you need to learn. Nobody knew anything when they started. And in fact, everything you learn is still not enough, because you're not supposed to relearn things we already know. You're supposed to find new things. So really what we should be encouraging in people is simple curiosity and perseverance, and those sort of personal habits that will really get you where you need to go. So it's much broader than physics and math, but do take those classes. It's hard to catch up if you drop the math.
Thank you. So Addison Boyette from Northeast High School asked, if there's a galaxy merges, if a galaxy merges, what did two black holes do if they meet? Did they fight for dominance, or do they merge?
Great question. Great question. So, yeah, each galaxy has a black hole. The galaxies merge. The black holes take a while to get near each other. They have to lose angular momentum. And they do that by basically colliding with other stars in the galaxy. So eventually they come close to each other. And then there's this period when they're just whizzing around each other. They're orbiting each other really fast. And at the very end, they're actually losing gravitational energy. This is the coolest thing about black holes. They're extremely, what Einstein would say are relativistic objects. That just means they warp space-time around them. It's as if you had a marble, but instead of space being ordinary around it, space is attached to the marble. And as you move the marble, space is moving too. So if you have these two black holes orbiting each other really fast, they ripple space-time. They make waves in space-time that travel at the speed of light outward. So very, very clever people, including Ray Weiss, and including, very importantly, Ray Weiss, have made an instrument called LIGO that can measure those gravitational waves. And we have now seen the gravitational waves from black hole mergers from about a dozen, maybe, actually they probably know about more, but they've published about a dozen black hole mergers that show, I should be careful, they're not looking at the most massive mergers that you would find from the supermassive black holes in the centers of galaxies, but they see smaller black holes merging. And interestingly, those things behave exactly as Einstein's theory of general relativity predicts. The gravitational waves are exactly as they predict. So we think that's happening also with the galaxy mergers and the very big black holes. Now, those we have not observed directly because you have to look at much lower frequency of gravitational radiation. And that means the wavelength's much longer. And that means you have to separate your detectors not by a few kilometers like LIGO, but by 1 million kilometers, which you can only do in space. So you have to put spacecraft, NASA has a plan for this, so does the European Space Agency, to send spacecraft into fly in formation in an orbit trailing the Earth. It's the most sci-fi thing ever. And those could detect the mergers of supermassive black holes following a galaxy merger. And the nice thing about them is that they last a year. The ones that LIGO finds last like a second, so it's over. But the ones that LISA will find, LISA stands for Laser Interferometric Gravity Observatory. No, that's wrong. That's what LIGO is. What is it? LISA. Space antenna. That's it. Laser Interferometric Space Antenna. LISA will see mergers of million solar mass black holes that last a year. So they'll be able to say, hey, there's a merger going to happen over there in about a year, and you can watch it. You can watch it. You can watch the center of that thing get bright, and so on and so forth. So that's going to be a lot of fun. And you guys are about the right age to work on LISA.
And let me just interject briefly to follow up on a point Dr. Urry made. We typically, as most of you know, we typically have a summer program where we gather at Mississippi State. Also throughout the year, we have a series of programs at various Mississippi universities. One thing, when travel restrictions are no longer in place, one thing we very much hope to do and plan to do is to go to see the LIGO facility that Dr. Urry is referring to, because it's actually right next to Mississippi. It's in Livingston, Louisiana, and Dr. Weiss, who spoke to us earlier, kindly offered to have us come to see it. And that is something that we very much plan to do. And it's just not far at all from Mississippi. It's right over the border in Louisiana. So I just wanted, so please, that's something to look forward to when school starts.
Okay, our next question is, I'm sorry, my thing's moved up. Oh, where did it go? I'm so sorry. What is the difference between a black hole and a wormhole, Dr. Urry?
Oh, yeah. So I don't know too much about wormholes. So wormholes are not something we have observed yet. They are, just as black holes were predicted by Einstein's theory of general relativity, wormholes are predicted by Einstein's theory of general relativity. They're essentially a solution to the equations of that theory. In the case of wormholes, they're like it's as if you took two black holes and connected them. Have any of you read A Wrinkle in Time by Madeleine L'Engle? Maybe. So she had it's a great book. I really like that book. In it, one of the people explains time travel as if you were, imagine you had a piece of fabric that an ant is walking on, a little bug. And you could take two parts of that fabric and just put them together. So the ant only had to go right there. That's how Madeleine L'Engle described time travel. So wormholes you can think of that way. If you have two black holes that are separated in space, but somehow connected through some general relativity warp in another dimension of space, then you could connect the matter from one to the other. Or I think the actual definition of a wormhole is a black hole connected to a white hole, where white hole is the term meaning matter is shooting out of it. So that, what I've just said is like 100% of my comprehension of this, which is razor thin. So if you want to know more about wormholes, you probably, well, you could read, there's a bunch of good books about it, but if you really want to know like how it actually works, you got to go into general relativity theory, which I have not done. So I don't know any more than I said.
I believe A Wrinkle in Time was also a movie recently.
It was, that's right. That's right.
If they don't want to read the book, they can watch the movie.
Yeah.
So speaking of time, Trendarius asked a question earlier. He asked, will time be different if you could travel through a black hole? And can a whole galaxy be trapped in it?
Oh, that's a really good question too. So actually all these are really good questions. So time would and would not be different. So one way in which it would be totally different is what you experience as the traveler going into the black hole is completely different from what your friend who is really far away and watching you, what they experience. So your friend would see you approach the black hole, but they would never see you go in it, because at the horizon of the black hole, time is infinitely stretched. And so according to the distant observer, you would never get in, okay? But according to you, the traveler going toward the black hole, first of all, the good news is you wouldn't even notice, because for a really massive black hole, where the black hole is much, much bigger than you are, there's no tidal force. So this is cool stuff. Okay, if it's a small black hole, like let's say, you know, the size of your town, if you were, you know, your left side was closer to the black hole than your right side, your left side would feel a much stronger gravitational force than your right side. And alas, you would be ripped apart before you fell in. So you would notice that. But the really big black holes, the million solar mass black holes, are so big that you are a point next to them. And so your left and your right feel the same force. And so you're not stretched. You're not the least bit affected. There's no crust at the edge of the black hole. It's not like an egg, you know, where you hit the shell. There's nothing there. It's just a location. So you would just go right in, and you would not even notice anything had happened. So you wouldn't get out. I mean, so you're done, you know, you go in, you can't come out, but you wouldn't lose anything. And to you, time would be progressing just at the normal rate you think it always progresses. The only way you'd see a difference is if you compare your clock to the clock of someone who's far away. Those clocks will not agree at all. That's another whole fun part of physics. When you study relativity and you find out that, you know, two things happening at the same time is not actually well defined, you and your friend can say, okay, look, there's some fireworks, 4th of July, some fireworks. Oh, that just happened. So you can agree it just happened. But somebody going by on a rocket ship would tell you it happened at a different time. There's actually no absolute clock. Very strange.
Okay, we're just going to take two more questions. And so one of them, Jacayla Cobbins from Humphreys County asked, what are some limitations you run into while studying black holes?
Yeah, I think we're not just black holes. I think we're always limited by how much data we have. We always, you know, we're always kind of working at the edge of what we can learn. And so, and we're always, because it's we can't go inside the black hole, right? We can only see what's happening right outside it, but we can do a lot. We'd like to have better cameras that can measure finer structure. We'd like to have, you know, the gravitational interferometer. We'd like to have different wavelengths. So there's more data that we could, it's kind of like, I mean, the analogy to say going to a doctor's office, and they measure a lot of things about you. They measure your blood pressure, they measure your temperature, maybe they take some weight and height measurements. And if you're really, really sick, maybe they'll do an MRI scan or some other kind of diagnostic imaging. So those are data, those are measurements which help a doctor figure out what's going on with you. They never have a perfect picture. They never have exactly all the data they want. And we're doing the same thing. We're getting a few bits of light from here and there. We'd like to see how that light varies in time. We'd like to see how it varies with wavelength. And those things allow us to model it with physics laws of physics that tell us what the underlying emission mechanism is, for example. So I would say we do our best to like figure things out, and then maybe 10 years later, there's a much better telescope and we can go look again and see whether we had it right or we need to refine our ideas. And typically what happens is when you get better data, things are more complicated than you thought, and you learn more. One of the things this is so ingrained, you know, I give a lot of talks to Yale alumni. This is how I met Matt. And I used to talk about how we found something that we were just totally surprised by, and it was totally unexpected and unpredicted, and how great that was. And I'm looking out at these lawyers, and I finally realized, to them, the idea that you were wrong is like a bad thing. You know, like a lawyer, you'd like to be right. You don't want to be wrong. But for a scientist, if you're wrong, that means you're finding something new, right? If you were right, then you already understood it. And if you're wrong, if you find something new that your idea doesn't explain, that's super exciting, because it means there's something new there that you need to figure out that will tell you something more. So we're always excited when we get more data and find out our past theories were not wrong, but let's say incomplete.
Okay, and our last question is there a possibility that humanity will be able to shift into space in the future? I'm so sorry. Is there a possibility that humans will be able to shift to space in the future? Are scientists studying ways to prepare that possibility?
Yeah, that's really interesting. There's certainly a lot of people working on living in space, exploring space. A lot of the science that's happening, a lot of the science that's happening on the space station is studying people's physiology to see what damage space does to you, both to your muscles, to your bones, and then radiation. Radiation in space is very dangerous. So, here I'll go back to, this is my sister calling. Hold on a second. Lisa, I'll call you back. I have not seen the movie Interstellar. Have you all seen it? Some of you? Okay. The reason I haven't seen it is when it came out, my buddy Neil deGrasse Tyson, tweeted something. So if you haven't seen the movie, the premise is the Earth has become uninhabitable. And so humans travel over here to this wormhole. They go in the wormhole, they find some planet, they terraform it, and then, people can go there and live. And Mr. Tyson tweets, this ruined the movie for me. He said, you make the Earth uninhabitable. You go through all this effort to go through a wormhole, find another planet, and terraform it. He goes, why didn't you just terraform the Earth? I mean, that other planet wasn't habitable either. Why didn't you just terraform the Earth? So your question reminds me of that idea. It's like, we certainly are poisoning the Earth. We are certainly killing all the species of animals on the Earth, many of them. This era is now called the Anthropocene because we're killing everything. So yeah, you could worry that we're making Earth so uninhabitable, we better find a place in space. But space is super, super unhealthy. There's no air. There's a lot of radiation. Gravity is our friend. We have evolved to live in gravity, and we don't travel fast. It'll take us a year to get to Mars, and that's the closest planet. So if you want to go to another solar system, anyway, what I'm saying is we better figure out, it's both a lot easier and cheaper and safer to figure out how to save our planet. This is where we live. This is where we've evolved. I think we should explore space. I think that's an interesting and important thing to do maybe, but not so we can escape the Earth, because it's a million times harder to make space livable than it is to keep our planet safe, or to make it well if it's gotten sicker. So that's, yeah, I would say let's try to fix where we are.
Okay. Well, thank you very much, Professor Urry. That was terrific. Meg has been part of our program from the beginning, really going back to 2016. I circulated a video, as a matter of fact, of Meg teaching some of our current tutors. And if you look in the class, Brian and Savannah are among the students in the class. So if you try to think, well, how can I do this? How can I proceed? Well, Brian and Savannah, who are now helping to teach you, were once in classes like this, and not too long ago. It may seem like a long time to them. It doesn't seem so long to us. So this has been terrific. Thank you, Meg. I do want to just note a few folks I saw join that we didn't acknowledge at the beginning. I mentioned our lead teachers. Thank you, Mrs. Creekmore, for leading that discussion. I mentioned Mr. Piegler, Lizzie, our coordinator. I also saw Mr. Azim, Ms. Anderson, Ms. Creel, Travis Reginald, who was among the people who first greeted Meg at Mississippi State. Travis is a graduate of Murrah High School in Jackson and went on to Yale. So again, he's somebody who has sort of blazed a trail, and we're certainly very proud and thankful for all that Travis has done. Dr. Wiggum, I think I saw her, Principal Gilstrap, Mr. Moore. I apologize if I'm missing others. So in any event, this was a great session. I think you guys asked terrific questions. I always get nervous if we're going to get enough questions and input, but you guys did a great job. We frankly had more questions than Meg had a chance to get to. For example, it's useful, Meg, somebody asked, why isn't Pluto a planet anymore? Which is a good question. But I know she needs to get back to her sister. We don't want to keep her further. So thank you, Meg. Thank you, everyone. Again, please, we do have our next session is tomorrow morning at 9 a.m. Please log in. I think we have another good session planned. Kieran, anything you want to add, or any of our tutors or teachers before we wrap up?
Just a big thank you, Meg, for being with us tonight. We so wish that we could have seen you in person, but we'll take this. We'll certainly take this. This was a really great discussion, and I'm glad all the students, as everyone has been saying, had such great questions and were very engaged. So on the point of showing up, as Mr. Dolan said, let's all show up tomorrow, bright and early at 9 o'clock, and stick with this. And if you haven't gotten around to doing your homework for tomorrow, get to that too. And yeah, I think that's all from my end.
Okay, Mr. Piegler, Mrs. Creekmore, Lizzie, anything further? Okay, well, thank you everybody for joining us. Thank you, Professor Urry, again. It was terrific. This is the 4th summer she's done this, so special thanks. So in any event, everyone have a good night. Sleep well, and we will get to work tomorrow morning. So thanks, everyone.
Thank you, everybody.